Welcome back. In this session, we are going to solve a problem on the application of Cauchy's residue theorem. So the first step is to find the poles and then find the residue of the function. And then after finding the poles and residue, then we evaluate the integral of the same function. And in this case, the circle is specified to be having radius 3, centered at the origin. So let's quickly go through the solution. So solution, poles of f of z are the solutions or are the roots of taking denominator and equating to 0, i.e. we have our function denominator is z minus 1 squared, z plus 2 equals to 0. This is the same thing as saying z minus 1 times z minus 1 times z plus 2 is equals to 0. So that is z equals to 1, 1, and z equals to negative 2. So i.e. the pole of f of z are z equals to 1. This is pole of order 2. And z equals to 2. This is a simple pole of order 1. So that's the first step. Second step is to find the residue of each of the poles. So residue at z equals to 1. Now, because z equals to 1 is a pole of order more than 1, then we use the formula residue at z equals to a is given by 1 over n minus 1 factorial times n minus 1 to the derivative of z minus a power n times the function f of z, and then this is evaluated at z equals to a. So our n is 2, so just be residue at z equals to 1 be now 1 over 2 minus 1 factorial. 2 minus 1 is just 1, so it just be d dz of z minus 1 squared times f of z. And then this is evaluated at z equals to 1. So 2 minus 1 is just 1, 1 factorial is 1, so this is the same as d dz of z minus 1 squared. F of z is given by z squared over z minus 1 squared times z plus 2. So remember, all these are done at z equals to 1. So these two brackets will cancel out. This bracket cancels out. So we'll have d dz of z squared over z plus 2. And don't forget that we are invested in the value of this derivative at z equals to 1. So here we'll use quotient rule to carry out this differentiation. Let this one to be u, this one to be v. So now it's u prime v minus v prime u divided by v squared. So our vu prime, differentiating this one, you get 2z multiplied by z plus 2 minus derivative of v is 1. So that would be just be z squared over z plus 2 squared. And then this, we evaluate it at z equals to 1. So replace where the z by 1. So we'll have 2 times 1 into 1 plus 2 minus 1 squared over 1 plus 2 squared. 2 by 1 is 2. 1 plus 2 is 3. 3 by 2 is 6. Minus 1. 3 squared is 9. So this is 5 over 9. So that is the residue at z equals to 1. Next, residue at z equals to -2. Now this one we use the formula limit as z approaches -2 of z minus 2 times f of z. So this will give us limit as z approaches -2, z plus 2, f of z is z squared over z minus 1 squared times z plus 2. And in this, you see that this bracket and this other bracket cancels out. So which will be limit as z approaches -2, z squared over z minus 1 squared. By direct substitution, we'll have -2 squared over -2 minus 1 squared. So this is 4 over 9. So that's the residue at z equals to -2. And then by Cauchy residue theorem, we'll have the integral of c of f of z dz is 2 pi I times residue at z1 plus residue at z2, which is the same thing as saying 2 pi I residue of the function at 1 plus residue of the function at -2. So integral along c of f of z dz, as per our calculations, residue at f of 1 is 5 over 9. And this other one we have gotten the answer to be 4 over 9. So which will give us 2 pi I as the integral along c of the function z squared over z minus 1 squared z plus 2 dz. So that is the solution to the specified integral. And remember, I've taken all of them because the circle was defined to having a radius of 3. So if you draw the circle, so this is 3i, this is negative 3i, this is negative 3, this is 3. So you have to have 1, negative 1, negative 2. So you see the points or the poles of this function were z equals to 1, and then z equals to -2. So all of them are within the circle. That's why we need the calculation for both. So therefore, be the solution to the specified problem. Thank you.